talk about this idea of finding limits. So limits is when we investigate what curves are doing as we're approaching particular points. There's different techniques. Quickest one, if you can do it, and you can't always do it, is direct substitution. If I wanted to know x plus 7, this function, what's happening to the y value as the x value is approaching 5? Well, because it's a straight line, it works quite nicely. I just substitute the number in and, well, the y value must be approaching 12 because the point 512 lies on the line. Not everything works like that. Here's one where we have to factorise and cancel. See, x squared minus 9 on x minus 3. That one is a line, but with a point discontinuity, it turns out, at 3, because of course the bottom of the fraction can't equal 0. In fact, if you were to do a direct substitution, you would end up with 0 on the top of the fraction and 0 on the bottom of the fraction as well. And that's one of those questions in maths. What is 0 over 0? Some people will say, well, surely it must be the number 1, because anything on top of itself is 1. We know that. Then others would say, no, it's got to be 0. Because when you divide 0 by anything, you get 0. And then there's another pool of people who would say, well, no, it's got to be undefined because you can't have 0 on the bottom of the fraction. So 3 different answers, and they're all logical. So what happens? Well, if we actually factorise and cancel, now the top of the fraction is the difference of 2 squares, and I can cancel the x minus 3. I now end up with a direct substitution, and we end up seeing that none of those 3 logical answers were actually correct. It's actually 6. So it's not any one of those 3 logical answers. They're not always what it's expected. This is the straight line, x plus 3. It's one of those ones with a point discontinuity in it. And that's where the point discontinuity would have been, at the point 3, 6. Now we have a very special limit. It all comes from the hyperbola, I guess is the easiest one to think about it. See, you can't substitute infinity into a function. How do you do that? It's not actually a number. It's just this idea of the biggest thing you could possibly have. If I said to you, what's infinity squared? Well, hang on, infinity is the biggest thing we could have. So how can I square it? And what would I get? Because clearly if infinity is the biggest number, and infinity squared has to be bigger, how can it be bigger than the biggest? It doesn't make sense. But we can work out a limit. And if you look at the graph of the hyperbola, as the x value is getting bigger and bigger and bigger and bigger, what is happening to the y value? Well, it's getting closer and closer and closer to 0. So this limit, we know, it will approach 0. We'll never get there, because you can't get to infinity. But we know what it's approaching, and this allows us to do some things. This sort of question, we saw this in curve sketching, where we wanted to work out what was the asymptote. Here's another way of working that out. We could look at the limits. As I say, if you try to substitute infinity into this sort of expression, okay, infinity cubed, well, that's got to be really big. Plus 3 times infinity squared. Wow, now it's even bigger. Plus 2 times infinity. Man, it's huge now. Minus 1. So what? But then we're going to divide that by 4 times infinity cubed. Really big. Minus 1. So I got this really big number divided by this really big number, neither of which I know what actually they are. What is the answer? Can't do it. So what we do is we divide everything by the highest power, in this case x cubed, because I want to get the pronumeral on the bottom of the fraction, because that I can work out. I know if I'm substituting infinity into the bottom of the fraction, then that fraction has got to approach 0. So I want to create something where the pronumerals are in the bottom of the fractions, only on the bottom of the fractions. If I divide everything by the biggest power, then it tidies up. And I've got all these fractions, but every one of them has the pronumeral in the bottom of the fraction. And so I know when not substitute in because you can't do it, but if I was to approach infinity on every one of those fractions, the answer's 0. And then I'm just left with a quarter. Bingo, I've got an answer. So if I was to draw this graph, I know there's a horizontal asymptote at a quarter. But here's the thing. I don't actually need to do this, because if the key is just the x cubed, I'm dividing everything by x cubed, then all I've got to look at is the coefficient of that highest power. Because have a look. Coefficient on the top was 1, coefficient on the bottom was 4. That is what I'm going to end up with, because if I'm dividing by the x cubed, that's what's going to turn into the constant. Everything else will go to 0. So I only have to look at that. So if I see this now, I can look at it and go, well, x cube's the biggest one. Everything else is going to go away. So I'm left with 0 on 1, which is 0. This one will approach 0. Here, highest power is x to the power of 7. If everything else was to go away, I'm left with a third. So that's the limit. X cubed on x squared. Everything else is going to go away. I got 1 on 0. That's undefined. So this one must be going off to infinity. It's one of those ones that keeps rising and rising and rising. Now I've got the question, find the horizontal asymptote. Well, we saw different ways of doing it. I could have done the polynomial division, for instance. That was one of the ways we saw it. But now I can say, let's expand it out. Oh, x squared's the highest power. Okay, what am I left with? I'm left with 1. There's your horizontal asymptote, got it straight away. Now if it's an oblique asymptote, that's not going to work, of course, because it'll say, oh, undefined, because an oblique asymptote, you're just going off to infinity. But horizontal asymptotes, it'll work every time. So in the handout, there should be a copy of the Terry Lee exercise, because as I say, our textbook, I don't think is that good on this particular idea.